Hi there. I'd like to tell you about lower bounds on the tunnel number of composite spatial theta curves. This is joint work with Maggie Tomova at University of Iowa. This is a talk I gave at Virginia Commonwealth University and is a much longer version of the talk I was going to give at an AMS sectional meeting that got canceled. So anyway, thanks for tuning in, as they say. All right, so I'd like to start with a bit of spatial graph terminology. So just like for knots, we say that two spatial graphs are equivalent if there's an ambient isotopy of three-dimensional space, taking one to the other. And for the purposes of this talk, I'm just going to work in the three-sphere, but pretty much everything I'm saying can be generalized to situations in pretty much any other three-manifold. Okay, so here's an example. On the left, we have a graph called the kinesthetic graph. And unless I screwed up my pictures and accidentally put a mirror image in, this spatial theta graph, there's an ambient isotopy taking it to this spatial theta graph. And you could draw pictures of the ambient isotopy by using Reidemeister moves, for example, if you wanted to. So for spatial graphs, this is the same notion as for knots. But for spatial graphs, there's another notion of equivalence that is not really that relevant to knots, and that's the notion of neighborhood equivalence. And there are two ways of describing neighborhood equivalence. One way is to talk about edge slides and isotopies of the theta graph, or really any spatial theta graph. And the way I'll show you an animation in a moment, but the way this works is, for instance, you could take this edge and slide it along this other edge and past the vertex and so forth. I'll show you a picture of that, but before I do that, I just want to say this is equivalent to talking about an isotopy of a regular neighborhood of the theta graph. So for instance, if we thicken the theta graph up, I'm not going to draw the whole thing. This. So if you thicken the theta graph, the spatial graph up, you get a handle body in three-dimensional space, and you could talk about an ambient isotopy of the handle body, and that's what we're calling neighborhood equivalence of the graphs. So neighborhood equivalence is closely connected to the theory of spatial handle bodies. All right, so I'm going to show you this animation. It's just a sequence of PDF slides, so it's a little clunky, but it should give you the idea. So I'm going to start by moving the red vertex here, and I move it along. So far, this can be described as just an ambient isotopy of the theta graph where we are shrinking that edge. But now I'm going to keep on moving. I'm going to keep on sliding. I'm going to slide the red vertex past the black vertex like that. And then I can do more ambient isotopies to unwrap the whole thing. Go ahead and straighten it out a little bit. Like so. And when I've done that, now what I have done is I've constructed a neighborhood equivalence from the theta graph on the left to this trivial theta graph. And this neighborhood equivalence can't be realized as an ambient isotopy because in the graph on the left, I have a non-trivial knot as one of my cycles. And in the graph on the right, every cycle is the trivial knot, is the unknot. So this was an example of neighborhood equivalence, converting a non-trivial theta graph into a trivial theta graph. Well, this actually suggests the possibility of constructing an invariant of knots, and actually I'll go ahead and extend it to spatial graphs. And the way that works is when we have our knot, we can say what's the fewest number of arcs I need to add onto it to create a spatial graph neighborhood isotopic to a trivial graph. In other words, a graph that lives in a plane or in a two-sphere inside three-dimensional space. The trefoil knot is not the unknot, so it can't have tunnel number 0. But when I attach, we've seen that when I attach this other arc to the top there, I create a spatial graph that is neighborhood equivalent to a trivial graph. And so we see that the trefoil knot, distort my slide there, trefoil knot has a tunnel number of 1, because that has tunnel number most 1 because there's a tunnel, and it has tunnel number at least 1 because the trefoil is non-trivial. The tunnel number of this whole thing itself actually has tunnel number 0, right? Because it itself is neighborhood isotopic to a trivial theta graph. Okay, so tunnel number has been pretty thoroughly studied for knots, less so for graphs. Oh yeah, here's another example. The Kinoshita graph that we saw earlier has tunnel number 1 as well. It is non-trivial, Kinoshita proved that, but when we attach this arc, we get something that is neighborhood isotopic to that trivial graph. Okay, whenever we have an invariant, especially a not invariant, we want to ask, how does the invariant behave under sums? And there's one bound that's really easy. We can say, okay, if I have two knots, K1 and K2, the tunnel number of their connected sum is going to be at least the sum of the tunnel numbers. And then it turns out we need a +1. Let me explain the +1. So we have one of our knots here, and we have another knot here, whatever they look like. To do the connected sum, I delete little portions of them. I band them together. And I notice that there is a sphere in 3 space separating the two factors of the sum. Okay, if I have a tunnel system for each of those knots, let's say that's the tunnel system for that knot, here's a tunnel system for that knot. I add those in, and I might think that I get a tunnel system for the connected sum. However, as I'm trying to do the edge slides and isotopies to turn this into something trivial, I might actually have to do an edge slide over the bit of the knot that I've deleted. So that says, okay, we possibly need to add in another tunnel like that so that I can slide over that bit of the knot. So the tunnel number of the connected sum is going to be at least the sum of the tunnel numbers +1. And Morimoto, Sakuma, Yokota, and Mariah Rubinstein showed that equality can actually hold. And again, I'm just talking about knots here, not more general spatial graphs. All right, what about lower bounds? Well, lower bounds are much harder because tunnel number behaves kind of erratically. Beginning with Morimoto, and then Kobayashi did a lot of work on this, and other people have as well. Noguera, Shermer, other people that have worked on this. The tunnel number can actually degenerate. And in particular, the difference between our upper bound and the actual value can be arbitrarily large. Okay, well, what are some concrete lower bounds? Trent Shermer showed that the tunnel number of a sum is going to be at least the maximum of the tunnel number of the factors. That's a fantastic result, but it doesn't really tell us if having more factors will drive up tunnel number. For that, we have to go back to the work of Sharlam and Schultens from 1999, who showed that the tunnel number of the sum of n non-trivial knots is at least n. In particular cases, we can do much better. Morimoto showed that if each of the knots is m small, and I'll not say much about that, which is a particular class of knots. If each of the knots is in that class, then the tunnel number of the sum of the knots is at least the sum of the tunnel numbers. Sharlam and Schulten's result implies an older result of Norwood's that tunnel number 1 knots are prime. Okay, what about spatial theta graphs? And turning to theta graphs because it's kind of the next easiest thing after knots, but certainly you could approach this question more generally. First thing we encounter is that there's more than one type of sum for spatial graphs. So what I think of as being the usual connected sum involves taking point on an edge of each of my two graphs and banding them together like that. If you do that to two theta graphs, you don't get another theta graph. But if you do that to a theta graph and a knot, you will get another theta graph. We also have this other operation of vertex sum. And you can do this with higher degree vertices as well, but that sum becomes very badly behaved under trivalent vertex sum. It's actually pretty well behaved. And the way that works is you take a degree 3 vertex in each of your graphs, and you delete the vertex and merge the edges together. There's a choice about how you join things up, but it's a result going back to Wolcott and actually really due to Berman, that if you orient your theta graphs in a particular way, the sum is going to be independent of the choice of orientations. But we don't need to go into that here. One reason why degree 3 vertex sum is so well behaved is because if you think about that it's a lot like connected sum. In particular, if you think about one of the cycles of your theta graph, for instance, there's a cycle here, and let me pick a cycle here. There's a cycle. The trivalent vertex sum actually acts as a connected sum on the cycles. Also, if we take one cycle and pass the double branch cover, the other arc lifts to a knot in that double branch cover, and the trivalent vertex sum corresponds to a connected sum on those knots as well. So there are lots of reasons to think that in general, trivalent vertex sum should behave very similarly to connected sum. Okay, well, what about tunnel number? Does it with regard to tunnel number? Well, again, upper bounds are pretty easy. If we have our two theta curves and we put degree 3 vertices to each other, we delete the vertex, merge the edges together. There's this thrice punctured sphere separating the factors. If we put tunnels in for each of the factors and add in an additional 2 tunnels, we see that the tunnel number is going to be the tunnel number of the sum is going to be at most the tunnel number of the factors plus 2 this time. Well, what about lower bounds? We might turn and first think about the Schalman-Schulten's lower bound. Just if I add together n non-trivial things using connected sums and trivalent vertex sums, must the tunnel number of the result be at least n? There's a result, an example of Yudave, Munoz, and Ozawa showing that the answer is no. So on what we have here on the left is I have a 2-bridge knot, a trefoil, and I've put a knotting tunnel in it, but I've done a connected sum with another trefoil. And you can do this with other 2-bridge knots besides trefoil knots. And so the summing sphere is right there. And if I go ahead and add in that red arc that you see, you can do the sides and isotopies we drew before to end up with this picture. And then you can do edge sides and isotopies to undo the knot down there. And so what we have here is a non-trivial connected sum that has tunnel number 1. Okay, and in particular, that means that we don't have a Schalman-Schulten's lower bound. Okay, that was the connected sum of a knot and a trefoil knot, and of a knot and a theta graph. What if I turn to just theta graphs? Well, here's an example where we have the Kinoshita graph that we saw as tunnel number 1. Here we have the same graph that we worked with before. This is actually an example of a 2-bridge theta graph, and they have a special role to play in what follows. So if I sum them together, I get an object of tunnel number 1 again. And I believe that this arc right there is a tunnel. Okay, now, one thing to notice is that we've seen that this theta graph actually has tunnel number 0. So maybe if we're aiming for some sort of additivity result, we like maybe tunnel number should be additive or most additive plus 2, something like that. Maybe the 2-bridge thing doesn't bother us too much. Well, here is another example. Here I have the trivalent vertex sum of 3 non-trivial theta graphs that has tunnel number 1. So again, we don't have the Sherwin-Schultens result. However, these 3 graphs that I'm summing together each have tunnel number 0. So somehow tunnel number has still gone up. It's not just adding things together, tunnel number 0. It's kind of fun to see how it works for this thing to be a nodding tunnel. And the basic idea is that using this tunnel, you can change that crossing. And so when you do that, what you get is, oops, let me do that in black. What you get is something that looks like this, that. Although I may have reversed those crossings there. But then we can just untwist this bit. And you end up with this picture. You can then do an edge slide going down there, and you get that picture. And then you can do edge slides and isotopies here to untwist all that, and edge slides and isotopies there to untwist all that. Okay, you can push this example a little further by taking additional sums right there and putting in these additional arcs. And what we do is if we take 2t plus 1 summands, we end up creating something that has tunnel number t. For what follows, it's going to be a little helpful if I relabel this a little bit. So let me call 2t plus 1 m, and then this is m minus 1 over 2. Well, the good news is this is about as bad as it gets. So here is our theorem. So if I have a spatial theta curve that I get by doing the trivalent sum of m prime theta curves and k prime knots, then the tunnel number is going to be at least m minus 1 over 2. That's the same quantity we saw before, plus k, plus the number of knots. Furthermore, we've seen that equality can hold. And when it does hold, then about half the factors have to be 2-bridge. However, we know that there are theta graphs like the Kinoshita graph or the vertex sums of copies of the Kinoshita graph that have tunnel number, where every cycle is unknotted. And it turns out that if you have a composite theta graph where every cycle is unknotted, then the tunnel number is going to be at least m, the number of factors. We also have a result along the lines of Morimoto's result that says that if each of these theta curves, or knots for that matter, is m small, then the tunnel number is going to be at least the tunnel number of the sum. All right, well, what's the key idea for proving this? And it relies on a knot invariant we created a few years ago. And actually, it's an invariant for knots, links, and spatial graphs. We call it net extent. And it takes values that are integers or half integers. If we're talking about a link, then in fact, it takes integer values. And in the context of working with things in the 3-sphere, if we have a knot that has net extent 0, it turns out that the knot is actually the trivial knot. So it detects the unknot. It also has the fantastic property that it's additive under connected sum and -1/2 additive under trivalent vertex sum. And then, I've claimed things about tunnel number, so there better be a connection to tunnel number. And basically, tunnel number is an upper bound for it. When we're talking about a knot, the negative Euler characteristic of a knot is 0 if G is a knot, and it is +1 if G is a theta graph. All right, so if we assume the existence of this, I can give you the idea for how to prove the main part of our theorem pretty easily. What we have to do first, which I'm not going to do in this talk, but show that not only does net extent detect the unknot, it actually also detects the trivial theta curve. So if you have a theta curve and its net extent is at most 1/2, in fact, 1/2 is the smallest the net extent of the theta curve can be, then so if it's equal to 1/2, then the theta curve is trivial. So once we have that, here's how the arithmetic works. So that we've seen that the tunnel number is going to be at least the net extent of our composite guy -1. That was the Euler characteristic business. Net extent is additive. So this is going to be equal to the connected sum of the net extent of the factors. But for trivalent vertex sum, it's actually only -1/2 additive. So I have to subtract the number of trivalent sums I've done, which is m-1/2. And I still have that -1 hanging around. The non-triviality means, appealing to the primeness of the factors there, says that the net extent of each factor is going to be at most 1, because it's at least, it has to be strictly bigger than 1/2 for the theta curves and bigger than or equal to 1 for the knot factors. So this is going to be m plus k, the total number of factors, minus m-1/2 minus 1. And I believe this all works out correctly to give me m/2. I have a +1/2 minus 1, so that's m-1/2 plus k. All right. So the natural question is, of course, how is this invariant defined, since I buried everything into that, the properties of that invariant. The way I like to think about it, although it's a little hard to write down precisely using this approach, but conceptually it's very helpful, is that we are going to think about different ways of building our spatial theta graph inside 3-dimensional space using handle structures. We're going to restrict ourselves to a very particular kind of handle structure, do some computation, and minimize over all possible ways of building. So the building blocks are in terms of handles, and so we have 0 handles, and there are 4 types. There's a 3-ball with no bit of the spatial graph in it. There's a 3-ball with an unknotted arc. There's a 3-ball with an unknotted tripod. And then there's this other piece, which is the 3-manifold part is a closed surface times an interval. And then I've picked some points in the surface and expanded them out to points times interval. The surface doesn't have to be connected, it just has to be compact, no boundary. I call the bottom side boundary minus and the top side boundary plus. Okay, so those are my 0 handles. For my 1 handles, they're all disk times interval, with the attaching region being the disk times the boundary of the interval. 2 types again, I have 1 handles with no bit of spatial graph in them, and I have 1 handles with a bit of spatial graph in them. And then I go ahead and I'm going to build something out of the 0 handles and 1 handles. So let me draw an example of how this might work. So some bits of spatial graph in here. maybe I have a knotted arc there, and maybe a tripod here, and another unknotted arc there. Now I go ahead and attach some one handles. So I attach one handle like that, maybe a one handle like this, another one handle like that. I can do more than one of those. That I can attach one handle like so. I could attach one handle like that. Another one handle here. Where I've attached to the endpoints of arcs, I need to go ahead and put in arcs like so. So what I've built is what we call a VP compression body. And again, I have boundary minus here. The one handles that attach to the surface times interval, I require that they always attach to the top. And so boundary minus persists, and then everything else we call boundary plus. So this is an example of a VP compression body. These are our building blocks. And here's how we put the building blocks together. So I'm going to do a schematic picture here. The big surfaces are boundary plus, and then I have boundary minus here. I'm just going to kind of group these things together. So this is one of my VP compression bodies. It contains bits of my spatial graph in there. Because my spatial graph can run through the cores of the one handles, I might have pieces that are disjoint from the thick surfaces, which I'll just schematically draw like that. Although how they sit in there is highly constrained by the method of constructing VP compression bodies. So I can start stacking VP compression bodies together. There are two glued along positive boundary. Here's one glued along negative boundary. The negative boundary can be disconnected. So I might have something like this. So so there's a pretty simple thing there. The curved lines just indicate that there is no negative boundary. This negative boundary right here, it is the negative boundary of a compression body, but it also belongs to the boundary of the manifold that I'm building. And again, the spatial graph, I've drawn only a few little bits of it, but it's sitting in there in the way constrained by the definition of VP compression body. Okay, so this kind of way of building with these things has shown up before in a somewhat different setting. So here's an example, and this is basically coming from Goodbye's theory of thin position that I'll say just a little bit more about in a moment. So what we have here is we have a knot, and there's a height function on the knot, so projection onto the z-axis. And as I move up the z-axis, I see that I have some minima, and then a maximum, and then another minimum, and then a max, a min, a max, a min, a max. And so what I do is I look at the spheres. These are the thick spheres. They have minima below and maxima above. That line is going through the maximum, but really the max should be down there. So the thick spheres have min below, max above. The thin spheres, like this one right here, has a max below and a min above. So in this picture, those thick and thin spheres are all concentric. And what I do now is, oh, right, so the thing to notice here is that this actually does decompose our knot into VP compression bodies. If you look at the bottom piece, for instance, there's the red thick sphere, and then there's a homeomorphism of just that piece, so that we see that each of those three arcs is unknotted. We have 3 bridge arcs there. This piece here is a concentric thin and thick sphere. The thick sphere is, I guess, kind of the one on the inside, and the thin sphere is the one on the outside. So that's an S2 times an interval. Okay, so what do we do to see what net extent is? Well, we look at our thick and thin spheres. Let me call this one H, for instance. And we take the negative Euler characteristic of H plus the number of intersections with our spatial graph. We take that whole thing and divide by 2. So in this particular example, the thick and thin spheres are all spheres. So the negative Euler characteristic of this H is -2. There are 6 punctures, so -2 plus 6 is 4, divided by 2 is 2. So we do this computation for all the thick and thin surfaces, and then I have an alternating sum where I add across the thick surfaces and subtract across the thin surfaces. And when you do that, you get 5. So here's a way of building this knot inside the 3 sphere using these VP compression bodies such that the computation gives us 5. The net extent of the knot is then just the minimum over all possible ways of doing the building, where we don't require the spheres to be concentric, and we also allow those. This example also has the property that there is there's no arc in any of these compression bodies that has both endpoints on a thin surface. We allow those too. So anyway, we look at all those different ways of structuring it, do this computation, add across the thick, subtract across the thin, take the minimum to get our invariant. Okay, so what's kind of the intellectual history here? I'm just going to give the briefest of outlines. So in the 1980s, A.K.A. introduced thin position, kind of what I've just shown you there, for knots in S3. And he did not use width, net extent, he used something called width, and was interested in the minimum of width. Schaumann and Thomson then extended this to apply to spatial graphs in S3, and also in a kind of completely different direction to handle structures on 3 manifolds. In the 2001, Hayashi and Shimakawa combined A.K.A.'s thin position for knots with Schaumann-Thomson's thin position for 3 manifolds, and really thought about things in terms of handle structures. They never had a knot running through the core of a one handle. That idea was introduced in 2006 by Tomova, and then the version I'm describing here is due to Maggie and me a few years ago. Okay, so what is the great thing about our kind of thin position? Well, if you remember, we have these, we've built our spatial graph out of these VP compression bodies so that there are thick and thin surfaces. In the 3 sphere, you can't have this picture because this has 2 thin surfaces being non-separating. That's okay. As I mentioned, this applies in a lot of cases. And when we have a composite spatial graph, there are these essential twice punctured and thrice punctured spheres that show up. And with our version of thin position, what happens is that there's going to be a set of thin spheres that give us a prime decomposition of our spatial graph. So actually, I should be a little careful. I can't have this one because generally for prime decompositions, you don't allow non-separating spheres. So maybe my prime decomposition is just those three thin surfaces. Okay, and so what happens then is you can split open along these thin surfaces and do the calculation. And when you have a twice punctured sphere, negative Euler characteristic plus the number of punctures divided by 2 gives you 0, and that's where the additivity comes from. When you have a thrice punctured sphere, you have -2 plus the number of punctures, so that's 3. -2 plus 3 is 1, divided by 2. So the thrice punctured spheres are contributing a half to the subtraction because these are thin spheres. And so that's where the -1/2 additivity comes from. Okay, so that gives you an overview of how our machinery can be used to study tunnel number of spatial theta graphs. For more, feel free to send me an email or take a look at the paper on the archive. Thanks very much.